Okay, let's see. Check this. Yeah. Yeah, so his question is about homework and due dates of homework. So you will only get credit until the end of the due date time. And then if you redo it after, you can use it for practice, but it won't change your grade on it. So if you do it and you got an originally a 0, then you'll still get a 0. The way to get the extra credit points is on that unit, and I will update that one too. Unit 3 practice problems, and then that one will replace the full homework grade.
I got full points on practice and like 0s on practice.
It should still keep the original, but I don't know. Let me know, I guess, or let the grader know if that does change. But yeah, I think it should still let you practice it. Who knows? Sometimes the system does funky things, but. All right, other questions? Anybody else have other questions? Okay, so again, there will be homework and quiz due. I'll get those posted tonight. I apologize for them being late, for being available. And it will be the quiz and the homeworks will kind of be based on the complex power. So it will ask you for calculations of what the complex terms are. So average power, reactive power, parent power, power factor, and shifts. So any questions on any of those? Okay. The next set of problems will also have that maximum power transfer where you need to find the Thevenin equivalents. And so I posted those problems. Any questions on those? Okay, let me know if you have any questions. Hopefully they're pretty straightforward. Do make sure to go through those and that you can do that type of a problem that will be on the exam. And then our next section is going to be parts of chapter 9 for filters. So that's kind of also what I'm going to go over today. So what I want you to take away from the filters is some terminology, some new terminology again. And so active versus passive filters, low pass, high pass, band reject. So being able to look at these to identify what kind of a filter are they. Corner frequency, so understanding what a corner frequency means. And then equation that is defined in omega. So understanding what omega means in a graph And so omega meaning radians per second. So it's a different radius than we're used to. So understanding that, and then understanding how to convert to hertz, which is a more common term for us. And then gain factor, resonant frequency, gain roll-off rate, bandwidth, and quality factor. So what I'm trying to get you to understand is just what do these terms mean? And how do I identify them on these graphs or pictures when I see them? So passive filters are basically just filters that contain only passive elements, resistors, capacitive, inductors, where an active filter has an op-amp. So just understand that concept. So that's the main concept there, is the differences between those two. So this is something to memorize. Blue. Okay, so active filters is with op-amps. Passive filters are passive elements, resistors, capacitors, inductors. All right, so the next thing that you need to understand is the differences between low pass, high pass, band pass, and band reject. So I want to show you, this is called a Bode plot. And what a Bode plot is magnitude versus frequency. So this shows you as I change my frequency, what is happening to the circuit output. So that magnitude is at the output. It is a comparison between the output over input, but if you want to just kind of look at it as output of a circuit, it is showing you what the value of the output is when the frequency changes. Okay, so x-axis is frequency and y-axis is the output of the circuit. So here you can see that once it reaches this value, if it was a square change, it would look like what that dotted line shows on here. But because it's not ideal, you're always going to see this little roll off instead. It's going to kind of curve down. The point where it's 1 over square root of 2 times that magnitude. What is that value? What does that look like? A number. Okay, 67%, but 1 over square root of 2. What does that remind you of?
RMS.
The RMS value. So this is the RMS value, the average value for AC signals. So when we reach that, that is the value we consider this corner value, or cutoff frequency will be another name you'll hear for it. Back up. So it's called corner frequency. Another term is called cutoff frequency. These mean the same thing. They are about 60 to 70% or 67 to 70% of what that maximum is. And that's the value of when we consider them like, okay, that's where it's changed. Mm-hmm. And so in the low pass, everything operates to that point. And then after that point, you don't have any output out after that frequency point. So we call this a low pass filter, where everything will be the same value. It's pretty much fixed at M0 until you reach that point. And then after that frequency, you won't get any output out. So this is called a low pass filter. High pass filter is same terminology. It will go until some frequency, and then after that frequency, then you will operate. So anything below that frequency doesn't pass through the circuit. So if I put in an input in when I have a 0 on that frequency, I don't get anything out. I get a 0 out, 0, or I put something in and I get 0 out. So if I am operating like at this frequency, and I expect to get 10 volts out or a 10 volt sinusoid out, I'm not going to get 10 volt sinusoid out if I'm operating at this frequency. Instead, I'm going to get 0 or about like 0.1 volt out with a sinusoidal signal on it. And I'll be like, well, what's going on? That means that my circuit doesn't operate in that frequency range. So a circuit will only operate in certain frequencies. It's real, like it's a real circuit. Ideally, yes, it could operate in any range, but all of them will have limitations based on either your components you put into the circuit or external factors of the chips themselves and the physical limitations of a chip. So those would be called parasitic effects that then affect the frequency of your circuit itself. So cutoff frequency or corner frequency, this omega C. What was the units of omega?
Radians per second.
Okay, good. Radians per second. And high pass is then, once I reach that corner frequency, everything above it, I consider it as operating correctly and that is where the circuit operates. So I would call this that the circuit operates about anything above that frequency. Low pass is it operates anywhere below the corner frequency. Band pass is where I only have a specific range. So this circuit is only going to operate between omega C1 and omega C2. And so this one operates only within a range of frequencies. So within those ranges of frequencies, this one I have 2 corner frequencies or 2 cutoff frequencies. So they're still called that term. And then that middle one, omega naught, is called my resonant frequency. So that one is also a new term, resonant frequency. So that is that omega naught term. Band reject is where it operates before the first frequency and then after the second frequency. So it works up to omega. So this would be considered from 0 to omega C1, and then everything above omega C2. So those would be the operating regions of the band reject. So these are the forms that the circuits make when I'm seeing different frequencies and how the magnitude will be. All right, so those 4 terms. And then for a low pass filter, M naught is considered the DC gain of that circuit. For a high pass filter, M naught is the high frequency gain. And then for the band pass, M naught is the gain factor. So those are all the same name for different filter types. And all they mean is the maximum amplitude that you get out.
So I'm seeing arrows that say idealize and actual. What's happening with those?
So ideally, a band pass is like a square, like, yes, once I reach this frequency, I go right up. So it's a square, but realistically, it can't be. And so it's more of a slope that you see on these. So you have the curvature to them. Okay. The other thing about the resonant frequency that you want to note is that the resonant frequency is when your input impedance is purely a real input impedance. So that also creates that resonant frequency value. Yes.
So at the
Uh-huh.
is it from omega? That's omega 1.
Yeah, so you would say that the circuit operates between omega C1. So between yeah, I don't know how to write that today. Between omega C1 and omega C2. So it has a range between these two. that operates between those two guys. Yes, so that just means that it has an input resistance of R. So you just have an R resistance input, but sometimes you can get inductance, you can have capacitance as an input impedance. So here it's saying that you get a resonance only when you have your input is just an R. So if you did like a Thevenin equivalent of your whole circuitry, you're only going to have a R equivalent on that input. Does that make sense? Okay. Other things. So these are some examples of bandpass filter responses. So this is one where you have, this guy again goes to like actual and real. So that curvature will change too. And so like here you have a poor selectivity when it's like really wide. And then, you know, medium selectivity to a very high selectivity. So you want usually for a band pass, you want usually a very narrow band region. And so usually you want that really high selectivity. And so you want a higher Q, which is the selectivity of it. So anyway, let's see. And then again, like for a low pass filter, again, you can get this Q range where you have like some resonance going on, and you can see in the blue line, like there's a little bit of a dip up. And then for Q10, you have, so the higher the Q, the higher the selectivity on that one location. For a low pass filter, it's not so great. Band pass, you want that high Q, but a low pass, you want it to just drop off quickly. And so you want a low Q for band, or for low pass, a high Q for band pass. So you kind of want to take those into consideration. And then for a high pass, again, the same thing, you would want a low Q typically, so you don't have a lot of resonance. So it just like goes up and pretty much looks just like the green line there. So you want a lower resonance on the low pass and high pass. And then on the band reject, again, you want a high Q. So the band reject and band pass, you want high Qs. The other two, you want low Q. So you just kind of want to know those terms so that when you're designing it, I'll kind of get into a little bit more about Q. Okay, so other terms that you need to kind of brush up on, omega is equal to 2 pi f. So remember that F is in hertz, omega is in radians per second. So to convert between the two, you can use this conversion. So radians is always radians per second, and F is in hertz. So to get frequency, knowing omega, it would just be omega over 2 pi. All right. Okay, the other equation that you're going to need is Q is actually determined by omega naught over B. And this will be an equation you'll have to memorize. Okay, so let's go through an example. So we want to know what type of filter is in the above circuit. We want to know, is it band pass or band reject? And so how do we even determine that? So the first thing you're going to do for these circuits is you're going to convert them into the Laplace domain, and then you're going to find what we call the transfer function. So do Laplace transform on the circuitry first, and then from there, find a V out over your input expression. And this is called the transfer function. And what the transfer function, it gives us an expression of our output for whatever input I put in there. So say your output over your input is 10. That means if I have an input of 1, I solve for V out in that equation, and it's just V out over 1 equals 10, then my V out will equal 10. So it's 10 times whatever V in is. So I'm just going to call this some, well, it's usually denoted big H of S. So this is in the Laplace domain. And then you transform it back into the time domain. So then your V out is going to just be this function in S or T, depending on which one I'm doing, and you multiply it by Vn. And so this is a really powerful expression. So typically this is what we look for in a lot of these circuits now, is when we're talking about AC, we're going to want this expression as the transfer function. Okay, so this becomes LS, this becomes 1 over CS, and then R's just stay the same. So again, I like node voltage, so I'm going to change this to node voltage, and I'm going to put my ground on the bottom. So it becomes V out over 10K plus VO over 30K. What is this one going to look like?
Yeah, times the over L.
So I can't just times it by, yeah, so because they're added on the bottom. So I'm going to have to kind of get a common denominator first.
How come when we transform those, we end up there faster, we don't solve for initial conditions? The breakbook, some source.
So now I don't know what the initial conditions are, so I'm going to assume they're 0. Unless I'm told, because I haven't actually even put on any power source. So I'm looking at kind of a generic input. So I'll make that assumption that they're just coming right out of the drawer and there's no initial currents or anything on them. So that is a good question, because no, we don't know. So we have to make an assumption. So it's kind of safe to say, since I'm generically hooking up different circuitry here for my input VI, and I'm doing it in terms of just a generic VI instead of like 10 volt, 10 sinusoid, whatever, that it is going to be 0 for that reason. Yes.
Do you know why we don't have V in the equation when we go over the 10K resistor around? We're just going to 0.
Oh no, I totally forgot that. Thank you. Yep. Sorry. That was not meant to stay in there. Oh yes. So V out or VO minus VI. I'm going to do it VN. I like VN better. Over 10K. Yeah, that was just my bad. Was there another?
If we don't have an input voltage or input source, how would we be able to solve for VN?
So we're doing it generically with just VN as a variable,
Okay,
and doing it V out over VN. And we'll get to there because we'll go there next. All right, other questions? Everybody see how to set up this equation? We're good? Okay, so now lump up VOs together. So I have 1 over 10K. And I'm going to do a little side here to get, so if I combine this with both of them to have CS on the bottom, then this is going to be LCS squared. plus 1 over CS. And this will be 1 over 30K, and then I flip the CS to the top. And so this bottom becomes LCS squared plus 1. And then I bring the VN over to the other side and then divide by all of this to get VO over VN. So this becomes 1 over 10K times 1 over. I'm just going to combine the 30Ks together. And that's my expression for V out over VN. So now I need to get like a common denominator for this one. And so the LCS squared plus 1 is going to be that times 30. So this is all going to be over 30K LCS squared plus 1 to make this a common denominator. So for this first one, it's going to be 3. And then this will be 2 times LCS squared plus 1. And then this will be 30K CS. And now this. And then that one will flip up kind of to the top. So I'll get 30K LCS squared plus 1 on the top. 10K times all of this. 3 LCS squared plus 3 plus 2 LCS squared plus 2 plus 30K CS. And the K's cancel, and then the 10 goes into this to just leave a 3 on the top. And plugging in the values for L and C gives me 3 times 40 nano times 10 nano S squared plus 3. And then on the bottom, I get 1.2 e to the minus 15 S squared plus 5 plus 0.3 milli S plus 8 e to the minus 16 S squared. Or do you guys like me to write? Here, I'll write these a little different. Ten to the minus 15. And this is 10 to the minus 16. Those might look better to you guys. Okay, so now I have, this expression. And this is called my transfer function. This is H of S. Oops, transfer function. And it is for any input. And now I can change this to give me a graph like the other ones. And I'm going to graph it with omega versus and remember this is an S, so my y-axis is J, so it's the imaginary portion. And so to get that, I substitute S equals J omega. And then I can rewrite this as 1.2 times 10 to the minus 15 J omega squared plus 3. 1.2 E, or sorry, 10 to the minus 15 J omega squared. So how would I graph this? This is a, so I have to put in a value for omega and then plot it on this plot, right? I'll get one value for each omega. So then I have to change the omega, get another point, do it in J omega and again, you know, and I'll get something for every single omega. So I can either use MATLAB to plot this, I can use anything else where I can put in a whole range of omega, and then I'm going to have to find the value for each one. That's kind of a tedious thing to do. So usually MATLAB's easier. 16 J omega squared. So in MATLAB, they have a nice tool. There it is. I can know I had it here somewhere. Okay. So you need what's called a control toolbox. So do note that you do need a control toolbox if you're going to use the Bode plot command. So you type S to tell it that it's a transfer function for your variable S. And then you just type out the equation H2. And so I put this equation in there. And I think in my notes, I have an error somewhere since the roots of the polynomial aren't correct. So here, from here, you can find the roots just like we did for the partial fraction expansion. So you can go and do that again. So you can find those roots and then go from there. But my numbers on this are not correct. So those roots are what's going to give you the corner frequencies or those cutoff frequencies. So from this graph, I'm expecting you to kind of know what is this? Which filter is this type? Correct. So it will be a band reject. So do you be able to identify those? In 2280, you're going to get into how to even graph these by hand and get into those details. So here, I just want you to understand where do you actually get this graph from. So I don't expect you to have to know how to graph these, but do know how to get the equation to graph them. So we're going to focus on getting the equation and then understanding what you get once you've gotten there. The other thing is how to use the information now from these. So from this, you can kind of get an estimated omega C1 and omega C2 here. Oh, let me explain this one. So this is called a semi-log graph. This is going to maybe be new to some of you. So this frequency, you can see how it is by tens, and this is a log scale. So the first, get in very here, but you can kind of see how these little, like each tick is more, like there's a big gap and then there's smaller and smaller and smaller gaps. That's because it's in a log scale on this side. So the x-axis is in a log scale and this is normal, a normal scale. Magnitude is in a variable called dB, decibels. You were actually right, decibels. And again, in 2280, you're going to get into that because decibels has to do with sound itself and how you hear sound. And so the level of a decibel relates to how much sound you actually hear. And so again, you'll talk about that in more detail in 2280. Just know that that is what the components of the graph, decibels versus radians per second. You can also graph this though in frequencies versus dB. So your frequency can be, instead of radians per second, it's in hertz. All right, so we can kind of make an estimate here of about 60%. So each one of these, sorry, let me go back to this one. So each one of these is like, if it goes, there's not a 0 in log, but you'll start at like 0.1, and then the next tick would be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and then 1. And then once you're at 1, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Then you go by hundreds in the next one. 100, 200, 300, 400, da, 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 till 1,000. Then you go thousands, 2,000, 3,000. So every tick depends on the first marker of what you're talking about. So if we're in 10 to the 4th, that's going to be 10,000. So now the next one will be 20,000 will be this next tick. Okay, I don't know. Oh, there it goes. Gotta go smaller. Okay, so this is going to be 20,000 for the next tick, 30,000. And then I'm, 40,000 until you get to 100,000. And then it's 200,000, 300,000, 400,000, 500,000, 900,000, and then 1 meg. Oops, 1, 2, 3, yeah, 1, 2, 3. Okay, and then it's 2 million, then 3 million, 4 million, 5 million, 6 million, 7 million, 8 million, 9 million, and then it's 10 million, so on. So each of these will be, hopefully that makes sense with the scaling.
Did you do an operation to like the function that is the graph to make it so that it's in like a log scale instead of doing a log scale on the bottom? You divide it by.
Do something to the values that are bottom.
So we interpret this graph with it in the logarithmic scale. And that is because it looks like a linear, like for the band pass and the band, high pass and low pass, it's going to be a smooth curve up and down. If it's not in logarithmic, it doesn't look like that. And so that's why we do them still in the logarithmic down here, so we can identify these patterns. And so that is the standard of why we do it. It's actually because our ear, Alexander Graham Bell, noticed that we actually hear logarithmically in a linear way. And that's why it translates it. So what is logarithmic is actually turns linearly. And so that is the relationship. So that's where dB conversion comes in, is it makes something that is logarithmic into a linear line. And so we can interpret it and then relate it easier. I know, cool, a cool thing, huh?
What's the map? The one with the scale one?
So the Bodhi magnitude actually does it for you. So that Bodhi plot command, that Bodhi mag of your function, it will already create it for you in the semi-log. And that's just because it is known to be a standard. That's like the standard format. So whenever you're given a Bodhi plot, it will always be in a semi-log x-axis. Okay. So we're going to make an estimate here of omega C1, like 70%, I'm going to say is somewhere around 10K. So this doesn't show it very well. Again, on MATLAB, it's a nice thing. You can take the cursor and actually click on the graph and you can move them to find these corner frequencies. So you can find where it's more flat and then you can go down let's see. In dB, it's actually going to be 3 dB shift equals the 1 over the square root of 2. And this is considered volts per volt. So a 3 dB, either up or down, is the same as that 1 over the square root of 2. So when you're looking for those corner frequencies, and you're shifting down, you just go 3 dB from where it's flat. And in the top, it would be an increase of 3 dB from where it's kind of more flat. So here you can't really see, but it's approximately somewhere around here. And when I measured it, this one actually came out to be 16.7 kiloradians per second. And over here, the same value is somewhere kind of up here. And actually clicking on this graph gave me about 150 gigaradians per second. Now that's not in the gigs, is it? Wait, 150, 10, 100. Yeah, that doesn't look right, but we're going to use this value anyway. Okay, so using those values, your B, which is your bandwidth, is going to be considered the region that you're kind of operating in. That's going to be between the corner frequencies for this one. So you're going to just take, so this is called your bandwidth. And it's where circuit operates. So you're going to just take, in this case, omega C2 minus omega C1. So 150 gig minus 16.7 K to give a value of approximately, 150 gigs still. And then remember that Q factor is going to be a resonant frequency over your bandwidth B. And in this case, that omega naught is right there at that value. Which looks like it's about 5, or let's see, 50. Yeah, we're in 50s there. So 50 mega radians per second over 150 gigaradians per second. So we get a Q factor of 1/3 milli. What did a low Q value mean? So that Q was how selective it was. So remember, This is selectivity value. So for a band reject, you want high selectivity. Meaning a high Q. And this is opposite that, right? 1/3 milli is really low. So Q of 20, Q of 50, that would be a high value. All right, questions on this? Right, that's all I had from that lecture. Let's see, what was 18? Okay. I'm skipping forward again. Let's see. Okay, so go ahead and work on this one to obtain that transfer function. And then, oops. And then for B, I'll show you the graph and then we'll talk about interpretation. So work on deriving that equation for that transfer function for this circuit. Oh yeah, I'm sorry. Might want those. Yeah, the numerator doesn't have anything in it.
Oh, yeah, you're such a. I would.
Yeah, we saw that.
Copy.
One. And then that.
So you're, for estimate, it's fun. No.
All right, so solving this, I set it up with using node voltage. So I use the top node as VO, and so VO minus VI over, and then I used, instead of S, I used J omega. And that's so that I can get it into terms for omega, just to solve for omega C. So omega C is going to be the root of my denominator. So you could leave it still in terms of S, and then you're going to get, you know, this value. So back to the equation. So V naught minus VI over J omega L, or LS, plus V naught over 1 over SC, or J omega C, plus V naught over R equals 0. And then manipulate that to get the ration of V naught over VI. And so that gives me the R's canceled. And so I have 1 over the square root of LC squared omega and J omega L over R. And then that term J omega C or J omega squared becomes omega squared. Anyway, the root of that gives me 10 to the 5th. And then I can plot this, which you don't need to know how to plot. So know how to use MATLAB if you do. You can just use MATLAB. So that gives me this graph. Which you probably already saw what it is, but okay. Brandon, move that so you can't see. Okay. So this is the graph. What do you notice about that graph? The blue line is the graph. What do you notice about? Okay, low pass, thank you. So it's a low pass, great. So low pass is identified. What else do you notice about the characteristics of this? What is going on with that? What does that mean when you have like that peak? Correct, so it's got some higher Q, which is not ideal for a low pass. Q is related to what? the bandwidth over omega naught. And so omega naught and the bandwidth. So how do you lower the Q here? Okay, I'm hearing both of them. Increasing the bandwidth would increase Q, right? So you would want to lower the bandwidth. What's the bad thing about lowering a bandwidth of a circuit? It only has a smaller range to operate in. So if that's a limitation, then that would be something to consider. That might not be something you have flexibility to do. Oh, sorry, it's opposite. Thank you. I'm dyslexic today. Love being sick. Okay. Omega naught over Q. So yes, it would be to lower the bandwidth. That's gonna, wait, increased bandwidth is going to decrease your Q in this case. Yes, that's what you want. So you would want to increase, which is actually probably might or might not be good for your application. It depends on what your limitations are. The other thing that you could look at is omega naught, which is going to be determined by the values of your components themselves too. And so omega naught is going to be, in this case, the value right here in the middle of that peak. All right. To graph this, this would be the MATLAB form of it. And again, you need to note that the control toolbox is needed. You may need to install that control toolbox if you don't have it already installed. And then, oops, just ignore this part. Okay, one other thing I wanted to mention here is there are what is called poles and zeros. So a pole, are going to be roots that are at the top part, numerator. Poles are roots of numerator. Or no, poles and zeros, sorry. You can have poles and zeros on both. Okay, sorry. Zeros are, okay, that was ugly. Zeros are the roots of the numerator and poles are the roots of the denominator. I went blank for a second, sorry. Okay. And then poles are the roots of your denominator. And these are going to be just specific frequencies where you're either going to have a corner frequency or a cutoff frequency, or are going to have a change in this graph. In this graph here. So we've only looked at filter graphs, but there are other forms of this graph. So one is a amplification graph. And so that's where you can have the changes that are not looking like a lower NE filtering. So with those, then the poles and the zeros are going to give you basically just a change in this magnitude graph. All right, any questions about any of this? Okay, I'm going to plug on since we have some more time. This one I'm removing. Wait. Okay, so the next thing we're going to move into is it's called Fourier. And there's first a Fourier series, and then we're going to get to Fourier transforms. So this is another, This is another technique, just like Laplace, that's going to give us a little bit different information. the things that I hope, like, as we've gotten into this section that you're noticing is that now we're talking about frequencies. And we've talked about, like, we can have any generic frequency input. If you guys remember back for phasers, phasers only worked when you had one specific input frequency. And so that was very limiting because you could only find it for one input. And then we moved to Laplace and we talked about complex inputs, but we didn't talk about the frequency ranges that they could be in. So this is the usefulness of Fourier series and Fourier transforms, is that now we can start to get a lot more information about the frequencies themselves and what frequencies can work within a circuit. So each of them kind of has its own uniqueness of why you want to kind of look at those things. And from a Fourier series, you usually are getting that more of that frequency information. So the first thing we need to do is to understand kind of some of the properties of Fourier series. And so what Fourier series is so a Fourier series, it will represent a periodic function with an infinite sum of sines and cosines. So now this gives you a really powerful thing that you can represent any signal. Doesn't matter what it is in terms of all these cosines and sines. And so a square wave that is represented as a sum of Fourier series looks like this, where it has a whole bunch of combinations of sinusoids in there. And it then looks like a square wave. Same thing for the sawtooth wave. It's just represented by a whole bunch of sums of these sinusoids. And any kind of signal that has some periodicity to it can be, and even there's some techniques to do it, even if it's not period, if it doesn't have a period to it. So anyway, they are represented by sums of sinusoids. So that is what a Fourier series does. And this is what a Fourier series looks like. It is literally a summation function with a whole bunch of cosines and sines in it. So the other really important thing about this is that these series can tell us information about how much contribution one particular frequency is in the circuit or in the signal itself. So this is really powerful. So this type of a frequency, or this exact frequency, its majority of the signal is that frequency. And I don't know if you guys have ever heard of this, but in power, it's really common to hear about some issues that happen where on the power line, it tripped this big motor somewhere. And they're like, well, why did it get tripped and what happens? And it's because these small little frequencies, and usually it goes down to even the fifth frequency that's like really low, but it's enough of a frequency that it will actually damage equipment and it will actually do things to different circuitry. And so you have to be aware of all of these small frequencies, especially in power. They call it a fifth harmonic that comes into effect. So any of you who've been exposed to that, you get this fifth harmonic is basically the frequency that is the fifth dominance in how much power there really is. So that small one that's down to like, okay, if this is my first one, this is my second one, third, fourth, I mean, it's a little effect, but even that fifth harmonic can actually create issues in power especially. And that goes to like damaging equipment. And so those are things that we want to know is how much impact does one particular frequency really have? And so that's why this is also another powerful technique. Okay. So this is an example of where I have a Fourier series and I'm trying to represent this signal. If I only have one cosine or one sinusoid, that's where the number B is. If I have two or three terms in that series, I get to C. When I have 10 terms, it looks like D. And when I have a summation of 100 sinusoids, it almost looks identical. And that would be like E. So you can see as you add up more and more sinusoids, I can get this to pretty much mimic any signal. And granted, I have to have 100 terms to make it look good. So that's where it gets to be also a trade-off. Like, do I need all 100 terms? And, you know, can I really model this pretty accurately with less than that? So that gets into like 3,500, ECE 3,500, where you're going to get into like, how many of these do I really even need to be able to represent signals and so on? And how many, like, how do I have to sample so much of a signal to be able to then like interpret it? So not going to be the scope of this course, but want to introduce you, you know, to these ideas. Have you guys seen Fourier series, Fourier transforms in math? I'm seeing some yeses. Which math did you see it in? Do you remember which math?
There was a simple that were about this.
Okay, but not on your, not in math class here.
Oh, well, there, yeah, I did see one on that JPEG instruction, Fourier, the inverse Fourier transform.
Okay. Do you remember which math class you saw that in? I'm curious to know. Anybody, you seen it?
At the end of our Q class, we started talking about it, but like we didn't really dive into it.
Okay, so math like 2250, or was that 31? Oh, that was even in 3150. Okay, so a lot of you may not even be there yet. Okay, so this may be your first introduction to what this Fourier series is. So do try to wrap your head around these Fourier series. We are going to get into more like details and actually like, how do we then like use this now to transform and solve the circuit with these Fourier transforms? So Fourier transform, just to kind of generically like high level understanding, is just like with Laplace. You have these tables and then you can go by hand and like derive all of the equations, but not usually what we do. We usually go to a computer and let the computer do it, or look up tables, use tables to do it. And so we'll be able to do the same thing we did with Laplace with the Fourier. And then we can interpret some of the information a little differently to get more of these frequency informations that are going to be useful for a circuit. All right, I will see you guys next Monday, and I will post the homework and the quiz by tonight so that you can start working on those too.
I think I might have had an idea.